So in lesson 2.5, we don't really need to worry so much about what the numbers are here, but what kind of these postulates, which you've actually already talked about because they are the definition of points, lines, and planes, and what makes them be able to have a line and where lines intersect. So these are all things that you kind of already actually know. So we're just kind of writing it into our postulate form. So through any 2 points, there's one line. So we would use that as our reasoning if we needed to. Through any 3 non-collinear points, there's one plane. A line contains 2 points. A plane contains at least 3 non-collinear points. So that one is very, very similar to the one up here, that if we have 3 points, we have a plane. Here, if we have a plane, we know it has at least 3 non-collinear points in it. And then the last one here, if 2 points lie in a plane, then the entire line containing those points lies in the plane. So again, if we have points on a line and that's in the plane, then we know that whole line containing those points is in the plane. All right, so let's go ahead and take a look here at example A. So exactly one plane contains points F, B, and E. Is that true? So let's see, where is F, B, and E? Well, those are 3 non-collinear points, so that is going to be true. A plane contains at least 3 non-collinear points. B, line BE lies in plane Q. Well, we have 2 points B and E, and those define a line. And since that both B and E are in the plane Q, then we can say that, yes, there's a line that is in that plane. So this one, through points F, B, and G, there's exactly one plane. So F, B, and G, that would actually be false, because if you notice, F and B are on the same line there, so that means that we can't have them be collinear. So non-collinear are the ones that form the plane. So this would be false because those are on the same line. The intersection of AC and FG. Well, if 2 lines intersect, they intersect at a point. So that would be true. 2 lines intersect at 1 point. So the reasoning is basically the definition of when 2 lines intersect, or when you have a plane, it contains 3 points. So that's kind of your justification, is that the postulate is that. So let's take a look at 2 more. If we have 2 lines that intersect, they intersect at 1 point. If we have 2 planes that intersect, they intersect at a line. So again, these are a review of stuff we've already learned of what happens. We're just now using them as postulates because they are definitions. So let's determine if this is always, sometimes, or never, and then explain. Our first one, if plane T contains 2 lines, lines EF and if plane T contains EF and EF contains point G, then the plane T contains point G. That's always. So if it contains that line within that plane, then anything, those points on that line are going to be in that plane as well. Okay. And again, numbers, this 2.6, 2.7, those don't really go with, because those change based on what section in the book they are. So the words is what we really want as our explanation. That's our postulate. What about this one? GH contains 3 non-collinear points. Does a line contain 3 non-collinear points? Never. Non-collinear points do not lie in the same line by definition. They have to be on the same line for them to make a line. There needs to be at least 2. So there's exactly 1 plane that contains points A, B, and C. Sometimes, but they must be non-collinear points, again, to make it a plane. So that's where we got to get sometimes, because it's not always, because it depends upon if those points are collinear or not. E and F are contained in exactly 1 line. Well, if we think about it, how many points do we need in a line? We need 2. So if we have points E and F, and they're then we have a line. So always, through any 2 points, there's a line. Okay. So two lines intersect in two distinct points M and N. Well, can we have two lines intersecting at two different points? No, never. Two lines intersect at exactly one point. That's the definition of the postulate. The intersection of plane M and plane N is a point. Well, planes, no. Planes don't intersect at a point, so that's never. They intersect at a line. On the next one, G. If A and B lie in plane W, then line AB lies in plane W. That's that one that if we have the points and they're in the plane, then we have the line that contains those points in the plane. So if two points lie in the plane, then the line containing those also lies in the plane. That's true, always. Line TR lies in plane M. Well, this could be sometimes because it depends on if those points, we got to make sure that those points lie in the plane, and then we can say that the line also. Otherwise, it could just be maybe one of them, and then it goes through the plane. All right, so make some flashcards. That's what really helps with those kind of definitions or postulate type stuff. All right, so now we're going to look at the proof process a little bit more here for our paragraph proofs. We've got our given, our hypothesis, and what can we draw a diagram, illustrate the information, state a theorem or conjecture to be proven is kind of our next step. Create a deductive argument by forming a logical chain of statements linking the given to what we're trying to prove, and then we'll justify kind of each of those statements with a reason, definition, property, postulate, theorem, and then we'll be able to finally state what we are trying to prove. Okay, so let's take a look at this first one here. So we're given that AC intersects CD, so two lines are intersecting. Write a paragraph proof to show that AC and D determine a plane. Well, let's think about this first. When two lines intersect, they intersect at a point, right? So we know we're going to have a point. Then we need to talk about how we have to have at least how many points for a plane. We need 3. So we're trying to use AC and D to kind of prove that there's a plane there. So let's take a look. We're given that A and C intersect at CD. And then we're trying to prove that A, C, and D is a plane. So let's start out with just talking about how they intersect at C, as A, C, and C, D are going to intersect at that common letter C because two lines intersect. Then their intersection is exactly one point. So we want to talk about that first. Then we can talk about point A that lies on AC and point D lies on CD. So those are 2 points that are not collinear. So points A, C, and D are not collinear because we know that A is on this line and D is on this line. So therefore, A, C, and D is a plane because it's got 3 points that are 3 points not on the same line. There we go. Because we got to have them not be collinear. All right, let's look at this next one. Given that M is the midpoint of XY, we're going to write a paragraph proof showing that those are congruent. So let's talk about what does it mean if M is the midpoint? What's that definition going to do? It's halfway, isn't it? So that's what we're going to talk about right away, is given that M is the midpoint, by definition it's halfway between the two endpoints of the segment, XY. So therefore, and you could even first state that xy or xm is equal to my and then do congruent by definition of congruent segments after that, or you can just kind of almost jump to right here and that works too. Excuse me. All right, so now we're going to talk about that once a conjecture has been proven true, it can be stated as a theorem and used in other proofs. So this one up here, this midpoint, we can go ahead and call it a midpoint theorem. So we can go from, if M is the midpoint of AB, we know this is congruent to this. So because we've already kind of proved it basically in the past. So let's take a look at this last example here, paragraph proof, starting out with B is the midpoint of AC, line AC, and point C is the midpoint of dB. So let's write a paragraph proof. Well, we can use what we just did up above. So that's what we're going to start with. If segment AB is congruent to segment BC and segment BC is congruent to segment CD by the midpoint theorem, then by substitution, we can plug in, or even transitive, could go from transitive, then AB has to be congruent to segment CD. And if they're congruent, they're equal by definition of congruent segments. Alrighty. A lot of processing, but again, follow these steps kind of that we talked about at the beginning here, of figuring out where you're at, where you're trying to go, maybe what you need in the middle, and then just kind of make your way to the end. And it just takes sometimes some processing and some reading through and some trial and error.